Okay, the second inequality is the Chebyshev's inequality. So for a random variable x with mean expected value of x and variance var of x, we have that the probability that the difference between the random variable and their expected value, this difference is greater or equal than c in absolute value. And this probability is less or equal than the variance of the random variable over the square of this constant c. This for any c greater than 0. Again, we can use the complement rule and have the other version, that is the probability that this difference between the expected value and the random variable to be less or equal than c. Well, in this case it's less than c. And this is greater or equal than 1 minus the variance of the random variable over c squared. This for c greater than 0. In words, the Chebyshev's inequalities essentially says that if a random variable, in this case we don't require the non-negative, has a small variance, then the probability that it takes a value far from its mean is also small. So if we have, for example, this random variable x, let's say, and had this PDF, something like this, if we have the expected value in the middle here, and we have some value c over here, this probability that the random variable is in this interval, the difference between x and c is greater, sorry, the difference between x and expected value is greater or equal than c, that is this region. If we have another distribution with a smaller variance, something like this, with a smaller variance, this probability that the random variable is far from its mean is going to be small if we have a smaller variance. Okay, the proof is this one. We fix the value c greater than 0, and we consider the non-negative random variable x minus the expected value square, right? And we apply the Markov inequality, applying the Markov inequality, but using a equal to c squared. Remember that Markov inequality, I'm going to put it here, says that the probability that x is greater or equal than a, this is less or equal than the expected value of x over a. Okay, so in this case, if we apply that to this probability, the probability that x minus the expected value of x, the square of this, is greater or equal than c squared. So here the c squared is going to be the a, and the random variable is this squared, x minus the expected value square, right? This is our x. So this is less or equal than the expected value of that random variable, x minus the expected value of x square, over c squared in this case. But this expected value here is actually the variance of the random variable, is the definition of the variance. So this is the variance of the random variable over c squared. And here, actually, if we take a square root on both sides, this is the probability that the absolute value of x minus the expected value of x is greater or equal than c, right? So finally, we have that the probability that this difference in absolute value between the random variable and the expected value is greater or equal than c. This probability is always less or equal than the variance of the random variable over c squared.